In our previous units, we discussed how to model things and objects. We talked about ER diagrams, or entity relationship diagrams, which we use with the structured approach. And we talked about how we show relationships between objects and how objects are, some of the different associations they could have with our class diagrams, for example, with aggregation and composition and so forth. And then we talked about the different attributes and how to determine those, and how we can identify things uniquely. So in this unit, our goal is to talk about how a database designer or a DBA or even a programmer is going to take those models that we've created and how those models would be used to create a database. Now, in this course, we don't really talk specifically about how all the other models are converted to computer code. We're a little less concerned with the actual code for the system itself than we are with the database. The database is really important. It's if you don't get your database correct with most information systems, if the database doesn't accurately represent the things that we have to, all that persistent storage that we talked about, and the information system is not going to be effective. And of course, the database also has to be able to enforce a lot of these business rules that we talked about. So lots of reasons to make sure we get it right. So we're going to talk about some of the different things that we have to do when we do a database design, and some of the things that we need to look for in good database design practices. So our learning objectives is to describe the database design process, the relational database model and what that is. I'm going to talk about normalization, which is really important for good database design, for effective database design, and to make sure that we have models that are going to be represented well in this physical database. We're going to talk about how we transform an ER diagram into the equivalent set of well-structured or normalized relations, or how we create a database out of that. We're going to talk about how we have to merge our normalized relations from separate user views into a consolidated set of well-structured relations. We're also going to describe the physical database design concepts, which are choosing storage formats for fields in our database tables. So we'll talk about that. We'll talk about translating well-structured relations into efficient database tables, how to use different types of file organizations to store these files on the computer, and the purpose and indexes of indexes and the important considerations in selecting attributes to be indexed. I'll talk about what that is and why that's important. So really just how we convert that ER diagram into our actual physical database. So we're still in the design phase. So actually, it's not still. We just arrived in the design phase with this unit. So previous to this unit, we were talking about analysis and all these different models and how we use those different models for our analysis and to get a better understanding of the system that we have and the system that we have to create. So in the design process, all of this is converted into an actual working system, right? Well, not converted to a working system, but converted to a design that could be used to create that working system. So this is another area that we're interested in, because it has to be done correctly. It has to be done, in a way that we're going to create an information system that's going to work well. And databases, like I said, are really important for that. We're also going to talk in design. Like I said, I'm not going to talk about how we actually code systems. I'll talk about that very briefly with implementation, but I am going to talk about forms and reports, user interface design, so the human-computer interface. We'll talk a little bit about that, and then we're going to talk about distributed and internet-based systems and some of the special design concerns we have about those distributed systems. So we'll talk about that later on in the section on design, and of course then we end the course with implementation and maintenance later on, which will go pretty quick. So for database design, there are file and database design occurs in two steps. We're going to develop a logical database model first, which describes the data using notation that corresponds to a data used by a database management system. And that becomes our relational database model, which is very similar to our ER diagram. In fact, it's almost exactly the same. And then we're going to use technical specifications for computer files and databases in which to store that data. So we're going to take that logical design and turn that into an actual physical database design, which isn't really that hard. I know it sounds like it's kind of hard, but this is really not too difficult. People do it all the time. This process of designing a database is kind of a mini SDLC in and of itself. In fact, if you ever took a database class, a lot of times in database classes they talk about the SDLC and how that relates to designing databases. They talk about how you start with planning, then you do some analysis where you learn about the data needs of the organization, and then you do some design where you put together your database diagrams, then you code the database and implementation, you build it in a database management system. and then you maintain that over time. So really, databases is a pretty large undertaking. In a lot of organizations, I think what you'll find is that is data management and the database is a whole team unto itself. In fact, one of the things we see a lot more now in larger organizations is you might have a development team working on an information system, and they're working with a database team that's wholly separated from the rest of the teams. So I work with a lot of companies where they have DBAs and they have database designers and database programmers that are all kind of separated. And one of the interesting things that's happened too is this concept of enterprise database systems, where instead of each information system having its own database management system, instead we have one large data management department, one large database system, like maybe it's SQL or Oracle, or maybe the organization has all of the major database engines. I've worked with companies that have, Oracle and Microsoft and MySQL. They offer all of those services within the IS department, and we're not building all those subsystems on our own with information systems. Instead, we're leveraging systems that already exist. And again, that's also something important to know in an organization, is which relational database management system or hierarchical database management system are they using to make sure that our systems comply with those standards and that they can fit well with what we're already using in the organization. So the process for database design, there's 4 steps in the logical database modeling process. So we are going to develop a logical data model for each known user interface for the application using normalization principles. Then we combine normalized data requirements from all user interfaces into one consolidated logical data model. That's called view integration. So we have to create one database model. We're going to translate the conceptual ER model that we create for the application into normalized data requirements. And then we compare the consolidated logical database design with the translated ER model and produce one final logical database model for the application or for the system that we're developing. So physical database design. So some key decisions we have is choosing a storage format for each attribute from the logical database model, which I'm going to talk about later on. Grouping attributes from the logical database model into physical records, and arranging related records in secondary memory, like hard disks, magnetic tapes. That's 1994 called, and wants their technology back. But in any event, we have to think about what these different storage media are going to look like. Selecting media and structures for storing data to make the access more efficient. And so forth. So these are all things that database teams will typically do. So our logical database design is going to account for every data element in a system, input or output. You're going to have normalized relations are the primary deliverable. I'm going to talk about what normalization here is in just a second. And then from those normalized relations, we get our physical database design, which converts those relations into actual tables. So we do our database model, which is really an ER diagram. So we create one ER diagram that, when we did our ER diagramming in our analysis phase, when we're doing our systems analysis, we weren't thinking about databases yet, which is a good thing, right? We don't want to think about that database technology yet. First, we want to design, what is a system that is going to work well for us, and what are the data needs of that system, and you develop that model. So a lot of the things that we do in that modeling step in the analysis phase, some of those things won't be in a database. They don't need to be persistently stored. Same with the class diagram, right? A lot of the things in our class diagram, like boundary classes and data access classes, those sorts of things, they don't need to be in our database design. They don't need to be stored in our database. But a lot of the things that we see in that diagram do need to be stored. And in addition, there's going to be some things that not only need to be stored in our database, but also that not only are not on that diagram that need to be in the database, but in some cases we have to change that ER model from the analysis phase in order to meet the requirements of a database model. There's certain things that you can't do. For example, the many-to-many relationships with associative tables and things like that, or associative relations rather. Some of that stuff is hard to do in a database engine, so the DBA will sometimes change that a little bit for it to work. But the reality is we got to make sure that works with the design, right? We can't just do whatever we want in the database. It has to support that design that we created in the analysis in the ER diagram. And we're going to convert that into our physical tables. So how does a database developer convert that into a database? A couple tools they have. They're going to code the definitions of the database. One of the coding languages that they use is the structured query language, or SQL. So that is primarily the language that's used to interact with databases and to define what's called data definition language to define those databases. I'm obviously not going to teach you about SQL in this class. You don't really need to know it for this class, but it's just good to know that these are some of the technologies that are used in database design. So the next topic really is the when we talk about the different types of databases, there are many different models for data storage, and the most predominant right now for most businesses is the relational database model. And this is where data is represented as a set of related tables or relations. And a relation is a named two-dimensional type table of data, and each relation consists of a set of named columns and an arbitrary number of unnamed rows. If you think about an Excel spreadsheet that has columns and rows, that's really a table, right? And in a relational model, you have this two-dimensional tables. And then, unlike Microsoft Excel, right? So if you go into Microsoft Excel and you create a table, right, in Microsoft Excel, you could create another tab in Microsoft Excel and have another table, right? You could have 5, 6, maybe even 50 tables in Microsoft Excel. But those tables really don't have any enforced relationship between each other. So when you think about your ER diagram or your class diagram is essentially has all of the what would become tables in our database. And every time you draw that binary association between two tables, whether it's many to one or one to many or optional to many or what have you, when you draw those lines between those two entities or those two classes in the database, those tables are going to be related to each other. And we talk about foreign keys and primary keys, and I'll explain what that is in a little bit. But those relationships have to exist in the database and be enforced in the database, and the relational database model allows that to happen. So again, if you think about Microsoft Excel, where you have these sort of independent tables of rows and columns, we have the same thing in a database. Really, it's really not all that different, except all of the tabs that you might have in Excel in a database, they would all be related to each other. And of course, we don't use it in that grid format that we see in Microsoft Excel. Most people don't use databases like that. They're just, they're getting information from it and working with information in some kind of application, which, I think most of us are familiar with that concept. But what's the important takeaway here is that the database has to support that relation, those relations that you found in the ER diagram, that you created in the ER diagram in the analysis phase, and it's the relational database model that allows that to happen. There are other database models that exist. There are database models that don't enforce those relationships, just good old-fashioned data models where the data is stored in text files, and I'm sure they could be related, but nothing is really enforced, and they're not using that two-dimensional data structure. Another example is hierarchical databases. So hierarchical databases are where we store all the information about things or objects in a single file. Each object might have its own file, for example, where we define everything about that object, or a set of related objects are all in a single file. These are things like Mongo and CouchDB and NoSQL and so forth and so on. And those models are certainly important, and they're gaining a lot of traction in some areas. I would say that at this point, those models are probably good for data warehousing, but we don't see them in wide use for production data and transaction processing systems because they lack some of the controls that we need, and they lack some of the reliability that we need in the relational database modeling or relational database model type systems. So they are out there; they exist for sure. So this should look familiar. This is an ER diagram. We learned how to do ER diagrams earlier. This is the type of diagram that's going to get converted into tables in our database. So for example, that customer, these are, when you look at the bottom, that's going to be our database tables where it says relations. So that customer entity becomes the customer table with a customer ID as the primary key, and we have a name and an address. And we're going to talk a little bit about how that gets converted to a database. So relations have several properties that distinguish them from non-relational tables. Entries in cells need to be simple. Entries in columns are from the same set of values or fields, and each row must be unique. So if you're thinking about Excel, right, every row in Excel would have to be unique in order to meet the relational database model. And a sequence of columns can be interchanged without changing the meaning or use of the relation. So in Microsoft Excel, you can't really change the columns around, but in a database, we can. In a database, the order of the columns is meaningless. It doesn't matter. It doesn't really change the meaning of the data. We don't have to worry about locking those columns in. And rows could also be interchanged or stored in any sequence. That also doesn't matter. And again, in Microsoft Excel, when you're making your rows, that might matter, right? You can't just move those rows around and display them any way you like, although there are tools to do that. But, if you think very primitively about Microsoft Excel, it's kind of difficult to do something like that. So a well-structured relation in primary keys, or a well-structured relation or table, is a relation that contains a minimum amount of redundancy. So you want the least amount of redundancy possible. It's going to allow users to insert, modify, and delete the rows without errors or inconsistencies. We'll always have a primary key, which is an attribute whose value is going to be unique across all occurrences of the relation. And all relations have a primary key. They must have a primary key. And this is what ensures that each row is going to be unique in our database. So a primary key may involve a single attribute. It could also be a composite of multiple attributes. Once we get to this point where we have our relations, which are essentially the entities from our ER diagram, we call them relations in the relational database model. So when you hear the term relations in regards to database modeling or in database design, relations are really just tables in the database, right? And a table is really sort of like an entity in our ER diagram or like a class in our class diagram. It's not always a one-to-one, right? It's not always that every entity in our ER diagram becomes a table in our database. Some entities will become multiple tables. Some entities are going to be part of another table. Some might get merged into a single table for whatever reason, depending on how the database designer decides to implement that based on the rules that you've defined in that ER diagram. As long as it's supported in the database, as long as the database supports the design that you created in the analysis phase, then it's certainly acceptable in the database as long as it meets the guidelines for database design. And one of those guidelines in database design is going to be normalization. So normalization is this concept where we convert complex data structures into simple stable data structures. So the result of normalization is that every non-primary key attribute depends upon the whole primary key. One way to think about normalization is sort of like, I don't want to say factoring, but getting the least common denominator, right? If you have a fraction that has huge numbers, you can reduce it to the least common denominator. For example, if you have 25 over 100, that becomes 1 over 4, right? Which is much simpler than 25 over 100. Normalization, we're kind of factoring down. We're getting to that least common denominator to have the simplest form of storing our data. The simpler it is, the least likely we are to have anomalies, errors, and other things, other bad things. There's efficiency problems that go away with databases when we have good normalization. In most database designs, we talk about 3 normalizations. We talk about the first normal form, which is unique rows and no multi-value attributes. Then second normal form, which is where each non-primary key attribute is identified by the whole primary key. And then third normal form, which is non-primary key attributes do not depend on each other. In other words, no transitive dependencies. And I know these are a lot of big words. I'm going to try to explain a little bit more about what this means. So a functional dependency is where we have a particular relationship between 2 attributes. So for a given relation, attribute B might be functionally dependent on attribute A, but for every valid value of A, the value of A uniquely determines the value of B, right? So we get like kind of these weird scenarios where different columns are dependent on other columns as opposed to the primary key, which is not good for databases. In second normal form, a relation is in a second normal form if any of the following conditions apply. So it's going to be a primary key consists of only one attribute. The non-primary key attributes exist in the relation, and every non-primary key attribute is functionally dependent on the full set of primary key attributes. I'm using a lot of big words here, and this is probably still pretty confusing if you've never been exposed to this before. But don't panic. I'm going to give you another slide here in a second. In fact, I think I'm just going to skip this slide and take you right to my other set of slides, which explain normalization a little bit different. So this is another way for me to explain normalization, and I'll do this with some graphics, and hopefully this will make a little more sense as to exactly what someone's doing when they're normalizing a data structure or a database for a system. So we're going to go from first normal form, which is going to eliminate repeating groups like lists of values, enumerated fields, or something like that. Then in second normal form, you're going to see me remove functional dependencies, which I just talked about. And in third normal form, you're going to see me remove transitive dependencies. So I'm going to show you what that looks like, what those 3 look like. So let's say this is our table, right? So we have a table of students in a class, for example. So here are 3 students. Now notice that that these students have 2 phone numbers, right? So this would be non-normalized. This is non-normalized. This is a non-normalized data table. Okay. My first step, and by the way, normally when we're creating databases, we don't have actual data to look at, but sometimes it's helpful to populate real data to see what it's going to look like, to give you an idea of how you can normalize a database, for example, or not so much how to normalize it, but you can see what it's going to look like once you start to implement it, and it helps reveal some of the issues that you're going to have that you have to normalize for. So in any event, let's say that this is a data table, and obviously I have more than one phone number in these columns. Well, one of the rules, the rule for first normal form, in order to get to first normal form, you cannot have anything repeating in the columns, right? No columns can be repeating of the same type of of the same data types, right? So if phone number is an attribute or a data type, I can't have more than one of those as a column, or else I'm violating first normal form. So I cannot have anything repeating horizontally across these tables. So I have to eliminate those repeats. And the only way to do that is to get rid of phone 1 and phone 2. But you'll notice what happens when I do that. Once I eliminate phone 1 and phone 2, I now am in first normal form. So this table that you see here at the bottom is now in first normal form. It's our first step. But when I look at this, I have a lot of redundancy in this table, right? Dan Mortimer shows up twice. Reggie Washington shows up twice. Luke Young shows up twice. All of these people in my address book show up multiple times, over and over again, because I have to repeat those phone numbers. So obviously this isn't ideal. So that's only first normal form. In order to get to second normal form, I need to eliminate these vertical repeating rows. So I eliminated the horizontally repeating columns in the first normal form to get the first normal form. Now I'm going to eliminate the repeating repeating rows in the vertical direction. So I'm going to look for where I could possibly, now this is where you start to see that having real data, putting some sample data in this table really kind of reveals, how this is going to look when I use it in the real world. So now I can kind of see that, oh yeah, I'm going to end up with multiple of the same person in my address book. So in order to eliminate that, first of all, I have to have a primary key, right? So there's nothing that identifies any of these rows. So I have to add a primary key. So this would be a surrogate key that we would create, for example. So I have an ID number. So what I could do is create a new table for the phone number, right? So I remove phone number from that table because that's what's causing the repeats. The phone number makes this repeat. So in order to fix that, I remove the phone number, put it in its own table, and notice that I have a foreign key now. So what I do is I reference the foreign key references the primary key in the table above. I can also, at this point, now I can see that I'm no longer going to have those repeating rows, so it's going to look like this now. So now if I want to find the phone number for Dan Mortimer, I just have to go look up his ID number in my phone records to find all of the matching phone numbers. So Luke Young, for example, has an ID of 3, right? That's the person ID. So I go find the foreign key 3 in the phone table, and I see his 2 phone numbers of 215-555-1000 and 2000. So I can see that, I can connect those tables together. And that's one of the most important things about databases, about relational databases, is that they have this ability to connect your keys. You can have a foreign key that references the primary key of another table, and that's how we connect our tables together. So in my design, right, so when I'm doing my database design, I would have a phone number table, and that phone number table would connect to my person table, and there would be a one-to-many relationship because my person can have many phone numbers. But that also tells me that there's a foreign key. Because they're connected, I know there has to be a foreign key to connect one to the other. And databases not only have these foreign keys, but the database engine knows what those foreign keys are and can enforce those foreign keys. So again, that's how we do this. So this would be in second normal form. Once you're in second normal form, the third normal form is kind of difficult because this one's not always as obvious. But if you look at this table, we have some transitive dependencies here. In other words, obviously the first and last name is dependent upon the ID number, right? only Dan Mortimer is the only Dan Mortimer that's going to have ID number 1, unless, of course, we have people with the same name, but let's not worry about that yet. So the problem is the address, city, and state that belongs to Dan Mortimer, that theoretically is not bound to Dan Mortimer. That address stands alone, right? Somebody else could have that address. So the address is not dependent on the primary key. That is a transitive dependency. It's not dependent upon that primary key. So I have to fix that next. This is what fixing the functional dependencies is, and the transitive dependencies. So I remove those from the table, right? So I take out the addresses and make a new table. I give all of the addresses an ID, and instead I put a foreign key. So now Dan Mortimer, I can look up his address by looking at the foreign key and going and finding that record on the other table. So when I go from first to second normal form, I'm creating a new table from columns, but I'm putting the foreign key in the table that I'm creating. But when I'm going to third normal form, I'm taking those foreign keys and I'm putting them in the table from which I created. So it's a little bit different, but it's the same concept. It's really not all that different. So at this point, we would be in third normal form. Theoretically, I could also make this table is now also in second normal form. So I could also make that table in third normal form. For example, the state. New Jersey appears twice, right? So that's another thing that's transitively dependent on something else. So I can remove that and create a state table, right? And give that a foreign key. I can even remove the city, create a table for that, and that becomes a foreign key. So this would be really, what you see here would be a fully normalized database. The problem is, if we go to that level of normalizing, there's so many tables with all of these different connections, all of these different all these different foreign key relationships. In order to write the code to reconnect all that stuff together to display it for a user or to work with that data in a meaningful way, it takes a lot of processing time. It takes a lot of effort to do that, and it becomes harder to understand it. We've reduced to that, to that lowest common denominator, but it also introduces some complication because we have so many different tables at that point. So a lot of times database designers will denormalize in order to get better performance on their database. So they're suffering too much performance loss because of all this normalization. They get really good control of their data, right? Normalization is great because we have really good reliability. We've got good data integrity and all that other stuff. But sometimes it just isn't going to be fast enough. So we have to denormalize to get back to the speed that we need for our database. So sometimes we'll reconsolidate things. So maybe this database would end up looking like this, instead of looking like the other option that I showed you where I split all those, the state, the city, and the state out to a new table. Maybe I'll just leave those alone, and that's good enough for me, right? That's good enough normalization. So that's pretty common. So you don't always have to look for perfect normalization. In many cases, we just don't go all the way because it would impact the performance too much. This is one of those judgment calls that database designers will typically make. They know what the ramifications of over-normalization is, and they can back it off to some appropriate level based on what their performance needs are, and also what type of data am I storing there, right? If we're storing financial data, in that case, maybe it's really important to have that control and that high level of normalization for reliability and integrity, but maybe for other record types, it's not as important, so it's okay. So once I have all of this done, right? So once I have all of this set up, so now I've got 3 tables, right? I took my original table, which was information about people, right, that are in my system, and I normalized that. Now I've got 3 tables that I'm going to use to store that information. So in a diagram, I would have to connect those tables. So my person table connects to my phone table, and my person table also connects to my address table. Now, if you recall, we did our one-to-many, zero-to-many relations, our cardinality or multiplicity, whichever one you call it, depending on the diagramming that we did, right? So it was cardinality in our ER diagrams. It was multiplicity in our class diagrams. You kind of have to do the same thing here. You have to define what that cardinality is. So what I would say is that, so my person can have 0 or many phone numbers, and my phone numbers can have one and only one person, right? Now, how did I determine that? So before, we were determining that by brainstorming it, right? So when we did this in the previous units, when we made our ER diagrams or our class diagrams, we looked at business rules, we used our own judgment, and we created this cardinality based on what made sense and what supports the business rules. In our database, we don't have the option to do that. We can't define this. Once we have a database structure like this, we don't say that this is a 0 to many and 1 to 1 relationship based on our own judgment. We do it because it's the only way it can work. So when you're putting that 0 to many and 1 to 1, whichever table has the foreign key will always have the many side of a something to many relationship. So that's why you see that I have the many, or the M for many. I probably should have used an asterisk to follow the UML guidelines, but whatever, I used an M. So the many side of the relationship is attached to the table that has the foreign key. And you can see that physically, this design supports that. That's how this works. So on my other table, right, so on the other side, it's going to be the opposite, right? My many relationship is going to be attached to that, again, to the table on the top, because that's where the foreign key is. So whoever has the foreign key, that's always going to be the many side of the relationship. So if you're looking at your ER diagram or your class diagram, and you're converting that to a database diagram, whichever side has the many, right? So if it's the crow's foot pointing to an entity, or whether it's the 0 ... star in a class diagram, that's the side that has to have the foreign key if it were going to be in a database. So you can do it either way. You can either say, let me just take my class or my ER diagram and just add my foreign keys based on which side has the many side of the relationship. And then from there, you can start normalizing if you wanted to. Or after you create these models or these tables, then you can start thinking about what the many relationships look like and then validate it against that ER diagram that we talked about before. So I kind of jumped the gun here a little bit, but when we talk about transforming our ER diagrams into relationships, so it's useful to transform the conceptual data model into a set of normalized relations. So we represent entities, then we represent their relationships, then we normalize those relations, and then we merge those relations, which is really what I just described, right? That we take that ER diagram and we basically try to figure out the relationships based on what our understanding of the business rules are. Then we normalize those relations, and then we merge those relations. So representing entities is pretty straightforward. Each regular entity is transformed into a relation for our database. So the primary key must satisfy the following two conditions. The value of the key must uniquely identify every row in the relation, and the key should be non-redundant, meaning it will never repeat. So the entity type label is translated into a relation name, right? Like a table name. Really, when we say relation, we really mean tables, right? So we're just going to translate that into a table name. So we talked about before binary one to something relationships, right? So the procedure for representing relationships depends on both the degree of the relationship, or the cardinality or multiplicity, and the whether it's unary, binary, ternary, and so forth. So a binary relationship is represented by adding the primary key attribute or attributes of the entity on one side of the relationship as a foreign key in the relation that is on the many side of the relationship, which I just described in the previous couple slides. So a binary unary relationship is represented by any of the following choices: adding the primary key of A as the foreign key of B, or adding the primary key of B as the foreign key of A, or both of the above. So you can do both if you wanted to, right? So in this example, we have a customer and an order. The customer has 0 many orders. So you can see in our relations down at the bottom, which are really our tables, right? Our primary key for customer is customer ID. The primary key for the order is the order number. And you notice that we have the customer ID is the foreign key in that second relation. So that's what's going to point back to the table above it, the customer table. Notice the many side of our relationship is the order table. And as I said before, whichever side has the many side of the relationship from our ER diagram is going to be the side that gets the foreign key. And you can see that's true in this case. This is how it was designed, which would be a valid design. So we can create another relation and include primary keys of all relations as the primary key in a new relation when we have many-to-many relationships. So we really have to resolve these many-to-many relationships by creating a new table. So in this case, we have a product and we have order, and then there's the ordered quantity, which is our associative entity. But in a database, it might look like what you see on the bottom, where we have the order relation, the product relation at the bottom, and the order line is in the middle. Now, since the order line would have the many on both sides, right? That has both the order number and the product ID, right? So that has the product that's on the order and the order number are both in that middle table. That middle table is the glue that holds together the many-to-many relationship. So we have to create that third table to support that associative entity. When you did your designs with your ER diagram, you may have, instead of using the associative entity, you may have already done this, which is typically what I recommend for designers. That I usually recommend that they do this early in the design rather than having to deal with this later on with the database design. But it's certainly valid to leave it like it is at the top in the analysis phase, and then in the design phase with the database, you would add that extra table to support that relationship. And this, of course, is what it would look like. For a unary relationship, really all you're going to do is add the primary key, and the foreign key is really a primary key back to its own table. So that's a recursive foreign key, which is perfectly valid, but it can only be done as a one-to-one relationship. But if you have a unary many relationship, then you have to model as one relation. You have to create a separate relation to represent the many-to-many relationship. So you have to create a new table. You're probably seeing a theme here that anytime we have a one-to-many relationship, we don't really have to create new tables to support that. But when we have a many-to-many relationship, we have to create a new table to support that. On the unary many-to-many relationship, of course, we'd have to do that. Our next step after we transform the ER diagram into our database diagrams, our next step is to remove any redundant relations. This is, of course, our last step in the logical database design. So the redundant relationships could come about due to multiple ER diagrams or user interfaces. This is done prior to physical file and database design. So first we remove these redundancies before we get to that physical database design. So given two relationships like employee 1 and employee 2, you can merge those together and it would look like this, right? So I took all the attributes of employee 1 and employee 2, I combined them, and that gives me the employee relation. I don't need to have an employee 1 and an employee 2, right? That's that's really not important to have two of those. I want to merge those because they're really all one entity in the database. A view integration problem, so we have to understand the meaning of the data and be prepared to resolve any problems that arise in the process. So one of the problems is synonyms, where we have two different names that mean the same thing. So when we're merging, we have to get agreement on a single standard name for the same thing. This happens in healthcare all the time. I'll go into a hospital and one department calls it a patient ID, another department calls it a medical record number, another department calls it a master patient index, but they all mean the same thing, right? So we have to all standardize to one vernacular. So that's what we're talking about here with view integration. Another example of view integration is homonyms. This is where a single attribute name is used for two or more different attributes. So we're all using the same term, but we all mean something different, right? That's going to be a homonym problem, and that also has to be resolved by creating some new name for that object so that it doesn't overlap with another object's name, because again, they mean something different. All right, so finally with view integration problems, we have dependencies between non-keys. So for example, suppose we have student 1 and student 2, and you'd merge it into just one student table. But if we have a transitive dependency where the major is dependent on the advisor, right, then we have to normalize this to move the major out to a different, or major advisor out to a different table in order to support that. And then we have classes and subclasses, right? So when we did our class diagrams, we had subclasses. When we did our entity relationship diagrams, we had subtypes and supertypes, right? Same idea. But a lot of times these relationships are hidden in user-of-user relations. So for example, we have patient 1 and patient 2, right? These are two. Now you might be tempted to merge patient 1 and patient 2, right? Because, oh, this is really the same thing. So let me just merge these together. All I have to do is, my new entity is going to have a room number and a date treated, right? And an address and a name, right? We just combine all that stuff together. But this might actually be a hidden composite relationship or a supertype and subtype relationship, for example. So, for example, maybe one of these is really an outpatient and the other one's really an inpatient, right? So we can't just merge them. We have to instead just call one patient and the other one inpatient, right? Or outpatient and inpatient or something like that. Okay? So, again, we have to watch out for those hidden subclasses and superclasses. Okay? All right, so this is what the normalized entity relationship diagram might look like for the example that's given in your textbook for hamburger company, the Hoosier Burger thing that's in your Modern Systems Analysis and Design textbook. If you're using that textbook, of course, sometimes I use different textbooks, so this might not correspond to your book, but this is just an example of what one might look like. So I'm going to move to, since I'm up to 40 minutes on this recording, I'm going to do a part 2 on this because I try to keep these under 40 minutes. So I'll do a part 2 where we're going to cover the physical file and database design.